Hello learners, welcome to this session of chemical equilibrium. I have already done two other sessions, chemical equilibrium part 1 and part 2. And this topic, chemical equilibrium, is very much important and there in your UG syllabus of CBCS, choice based credit system of BSc General. Now, in the previous sessions 1 and 2, we have covered the initial parts of the discussions, that is, we have discussed what are reversible and irreversible reactions, then chemical equilibrium as a dynamic equilibrium. Then we went into seeing what are the conditions for chemical equilibrium to happen and the spontaneous reactions. Then what are the various stories regarding the discovery of chemical equilibrium by Berthollet. Then next we went into the thermodynamic discussions regarding the chemical equilibrium situation, like what happens to the Gibbs energy change under standard conditions. Then we also saw that not always if the Gibbs energy change is 0 for an infinitesimally small change, the reaction does not occur. This is not true with several examples we have gone through. Now, we will come in this session, we will discuss about the equilibrium constants regarding the chemical equilibrium. Also, you must recapitulate what we did in the last session, especially about the reaction quotient and chemical equilibrium constant K. What is the relation between the reaction quotient, a very important concept, and the chemical equilibrium constant K. I hope you have followed the previous sessions, and myself, Professor Kamalika Banerjee of the School of Sciences, IGNOU, Indira Gandhi National Open University, I welcome any queries, any questions regarding the previous units, previous sessions also, and please post your queries, if any, in my email, that is Kamalika, Kamalika @ignou.ac.in, or you can post your queries in our blog WEAS, which is there in the School of Sciences website, you will find in the IGNOU website. So, let us now come to the equilibrium constants Kp, Kc, Kx. We have already done in the last session, as I was telling, the concept of equilibrium constant and also the concept of reaction quotient. Now, we will go to what is these subscripts when they are added, Kp, Kc, Kx. So, equilibrium constant for reactions, these are not only in gaseous system, but in solutions also. Now, with K, when we are applying this P, C, X, it denotes these constant expressions have partial pressure, molar concentration or mole fractions. Now, first we come to this Kp. For reactions involving gases, it is convenient to express concentration of any gas at any given temperature in terms of its partial pressure. To define equilibrium constant in terms of the partial pressures of the reactants and products, you have to start with this equation number 14, which is shown here. And again I repeat, these stoichiometric coefficients are there here. What are they? We have done in the previous sessions. Do recapitulate from there. And we have used alpha, B, C, D. Why we have used alpha? Because generally for small a, we denote activity. That is why. Now, here Pa, Pb, Pc, Pd, these are the partial pressures of A, B, C, D. Now, at equilibrium, these are the stoichiometric coefficients, and we can write Kp like this. You remember, we have done in the equilibrium constant, first the numerator will have the concerned terms of the products and the denominator will have the concerned terms of the reactants. So, same way here, the partial pressure of the products with the they are raised to the power of their stoichiometric coefficients on the numerator, and in the denominator we are putting the reactants with their stoichiometric coefficients. If you look at this equation 15, then you must be knowing that this Kp is the equilibrium constant in terms of partial pressure, which is constant at a given temperature. And this equation 15, this is valid only for ideal gas systems. So, at equilibrium, del G naught Tp equal to minus RT ln Kp equal to minus 2.303 RT log Kp, where T and P are temperature and pressure. This relationship is known as the Van 't Hoff isotherm. This equation 15, which we dealt before, can also be written like this. The coefficients of the denominator may be taken as minus and we can put it like this. Now, all these equations 15 to 17 which are shown here, these are depending on the dimensions of Kp. They depend upon the stoichiometric coefficients of the reactants and products. Now, equation 15 we saw. Now, that equation let us see with this example. You remember, this is the equation 15, and now we are going to see an example regarding this. Now, see, for a particular experiment at 1000 Kelvin, it is found that these are the values for the partial pressures of sulfur dioxide and sulfur trioxide, where the reversible reaction sulfur dioxide plus oxygen gives sulfur trioxide. This is the reaction. Now, we have to calculate Kp, where you are given the partial pressures. So, this is the solution. At a given temperature, the Kp value, see the Kp value, it will be at a given temperature equal to this, following equation 15 to 17, and so we get the calculation done and you will get the value of Kp. Okay? See the unit, which ones are cancelling and which one is remaining. You have to be careful about the unit of the Kp. Okay? Next you see Kc. This is the equilibrium constant of the particular reaction, which is the ratio of the concentrations of the products to the concentrations of the reactants. Always the products will come on the numerator and the reactants will come in the denominator for equilibrium constant. Now, the subscript C, it is the equilibrium condition which is expressed in terms of the concentration units, that is moles per liter of the various species. So, you get Kc, you can denote it like this in terms of concentration, C raised to the power of the stoichiometric coefficients in the numerator and denominator raised to the power of the stoichiometric coefficients of the reactants, and C is the molecular concentration. Similarly, if you take Kx, the mole fraction x, taking the equilibrium constant in terms of mole fraction, then you will be using this term 19 equation, where Xc to the power C, again the products are coming in the numerator and the reactants are coming in the denominator. Xi is the mole fraction of the species I. Now, according to Dalton's law of partial pressure of an ideal gas I is given by Pi equal to Ptxi, where Pt is the total pressure and Xi is the mole fraction of the gas in a gaseous mixture. So, we can write this Pi is the partial pressure of the ith species, that equation 19, we can rewrite it like this, where we had given the Kx, this one we can write now in terms of partial pressure. Okay? So, then we get this equation 20. In terms of mole fraction, if you find out the equilibrium constant, then from 19 equation and this relation partial pressure of ith species equal to Xi Pt, we can write down this. So, now next, once we have studied what is Kp, what is Kx, what is Kc, we must see, is there any relation between these three equilibrium constants Kp, Kx and Kc. So, that is what is our aim, to find the relationship between these constants at a particular temperature, and this is there with the ideal gases. For any ideal gas, the pressure is given by this equation 21, P equal to N by V RT. Now, V is the volume occupied by N moles of gas at temperature T, the absolute temperature. So, N by V, if you look at it, is nothing but the molar concentration C. So, you can write P1 equal to N1 RT by V, which is equal to C1 RT. Look at this equation 22, where Ci is the molar concentration of the ith species. Now, if you substitute the value of P in equation 15, you remember this equation 15 which we did before, here this equation 15. Now, here if you substitute the value of P, then what do you get? You get in terms of C, and this is the equation which you get 23 at the end, where P is replaced by CRT and the whole thing is raised to the power of the stoichiometric coefficients. You see the C here is nothing else but the molar concentration, and the subscript C and the superscript C, do not be confused, that they represent the element, the product C, and the superscript C is the stoichiometric coefficient. So, thereby you will get Kp equal to this value, this 23, and now you remember Kc is nothing else but Cc to the power C, Cd to the power D, Ca to the power alpha and all this. So, you get Kp equal to Kc into RT to the power delta N. Look at this, the 23, you see the left side of the right hand side, the left side of that is nothing else but the Kc, and the other part RT raised to the power, what is it? Nothing else but the C plus D minus alpha plus B, which is the change in the number of moles, that is del N. It is equal to the mole of product gas minus mole of reactant gas. Now, if del N equal to 0, then number of moles of reactants is the same as the number of moles of products in gaseous phase, and then you will get Kp equal to Kc. Okay? Next we come to the relation between Kp and Kx. Again, this is the equation 15 which we discussed already. In a gaseous mixture, the partial pressure of the component A, Pa, its mole fraction XA and the total pressure P are related as this. We have already done this. Similarly, you can write for PB, similarly you can write for PC and PD in terms of partial pressure, mole fraction and total pressure. Now, in this equation 15, this is the equation 15, if we substitute all these values instead of partial pressure, if we write them in the terms of mole fraction and total pressure, we will get this equation 26, isn't it? Look at it carefully. We have substituted wherever the partial pressure was there, we have substituted with mole fraction into total pressure. So, if we take on one side all the mole fraction values and keep on one side the terms involving total pressure, we get this 26 equation, which is nothing but you see the left side of this right hand side part of this equation 26 is nothing else but the equilibrium constant in terms of mole fraction, and then P raised to the power C plus D minus alpha plus beta, which is nothing else but delta N, as we did in the previous relationship. So, we get this, that in this equation 26, where P is not equal to 1 atmosphere, we will get this, that is it will become Kx. You see here, if you put 1 instead of P, that is at 1 atmosphere, then it will become nothing else but Kx. So, Kp equal to Kx into P total by P naught to the power delta N. That is the equation 27, the relation between Kp and Kx. You should note here that Kc and Kp, they depend on temperature, but Kx depends on the total pressure and temperature. Okay? This is something very important. With the help of this next example, you will be able to understand how you can do the conversion very easily from Kp to Kx. You see this example 3, how the equilibrium constant depends on the form of the chemical equation. This you will see here. Let us take the equilibrium system of hydrogen, nitrogen, ammonia. You know, this reaction you have already done in chemistry must be the Haber's process of ammonia synthesis. It is a very important industrial process and it has been studied in great detail. The equilibrium has been studied in great detail to understand how to lower the cost. I have told you in previous sessions also regarding chemical equilibrium, that why the study of chemical equilibrium is so much important for human civilization, for industries. This is the reason they want to study where you will get the yield best under low cost conditions. And here is the system of nitrogen, hydrogen and ammonia, where you have to study the equilibrium. So, you can write it in various ways as shown. You can write nitrogen plus 3 hydrogen gives 2 ammonia, or you can halve it, then it will become 3 by 2 and ammonia no coefficient, and you can write it in the reverse way also. We have already learned in the previous sessions that you can arrive at the chemical equilibrium from any side. The equilibrium composition will remain the same for the same temperature pressure conditions. So, here you are arriving at the equilibrium from the other side, that is the product side. 2 ammonia gives 2 nitrogen and 3 hydrogen. Now, the equilibrium constant for the first reaction here is 0.19 at 532 degrees centigrade. Now, you write the equilibrium constant expression and calculate its value for the other 2 reactions at the same temperature. Now, first you must write the equilibrium constant expression, then examine the concentration terms to determine the relationship between equilibrium expressions. Then you must utilize these to find the relationships between equilibrium constants. So, write down the equilibrium constant first. So, product on the top to the power of the coefficients, stoichiometric coefficients, and denominator will be the reactants with their stoichiometric coefficients. K2 will be again as we have halved it. So, this will be the expression, and K3 the third one where we are arriving from the product side. The product will be the nitrogen hydrogen here. So, they will be in the numerator and ammonia will be in the denominator. Now, if we look at K1 and K2, then we see K1, if we halve it, halve the K1 on top and bottom. So, you see it is K2 raised to the power 2. Okay. So, next you must see K2 square, that is nothing but K1 and that is 0.19. So, now K2 you can find out from the square root of 0.19. So, when the stoichiometry is halved, the new K is the square root of the old K. Third equation is the reverse of the first. So, now K3 is the old K1. So, if you reverse it, that is 1 by 0.19, 5.3 is the value, we can see that we get the third equilibrium constant. So, each value of K can be applied to a specific form of equation. Similarly, if we see this PCl5 and you have to calculate Kc, the Kp is given. So, this is the relation Kp equal to Kc RT to the power delta n, and this is the solution you have to give. You have to find out the Kc. So, Kp by RT to the power delta n, and if you substitute the numerical values, you will get the value of Kc. So, in this session, we have, apart from the previous sessions, we went into reversible, irreversible reactions, chemical equilibrium, general expression for the equilibrium constant. Here we have done the relationships between Kp, Kc, Kx. So, you must be able to do such any problems that you face, you must be able to solve. Like you are given Kp, you have to find Kc, or the vice versa, or the Kx. If you are given the correct values, the correct requirements, you can definitely do it. So, start practicing all these problems which I have already discussed, and you can also search other books for problems, and I hope you are now following how we are going in the chemical equilibrium part, starting from the dynamic equilibrium to the concept of the thermodynamics in chemical equilibrium in the second session. Now, in third session we and also in the second session we went into the reaction quotient and chemical equilibrium, its relation Q and K, what you understand from the value of Q, what you understand from the equilibrium constant K. And in this session, this third session, we have done the different equilibrium constants in terms of P, C, X, and we have tried to give the relationship between them so that you can also do problems regarding these, the conversions. So, this way do study chemical equilibrium according to these topics, and if you have any queries, you can mail me at Kamalika, Kamalika @ignou.ac.in, and also you can post your queries in our WEAS WAS blog in the website of School of Sciences, and which is there in the IGNOU website. Thank you, learners.